Okay, so welcome to this is session 3 of VMCAI. And to keep you awake after lunch, there is a bit of everything in this session. There's security, privacy, model checking, and synthesis. So the first talk is Joachim Barth on automatic and incremental repair for speculative information leaks. Thanks.
Thank you for the kind introduction. This is joint work with Swen and Yakir. And I want to start first with introducing the attack that we're actually looking at. And this is the Spectre attack that was published 6 years ago. And if you have a simple code example that just gets an index I and does a bounce check, that actually the access in line 2 is valid. Now if we add speculative execution to that, we might actually execute the then branch, although the condition is not satisfied. And I depict that here with this execution that I will build up. And on the right, you see a model of a simplified cache. So we start in line 1. And even though the condition is false, we will enter the then branch and execute line 2. Now, this means that now in cache line B, we actually get the access to A. And because this is now out of bounds, meaning this might be any secret that is accessible to the program. And then we use that value, compute a bit, and do another access to another array. Now in this case, we just say this accesses cache line D. And what's important here is that an attacker can analyze the cache in a way that knows which cache lines have been accessed, and so in a way the secret key was been encoded in this cache line access. And if the processor now realizes at some point that there was actually some misspeculation happening, it will go back to line 1 and do the correct branch, which is just skipping to the end. But the important part here is that we don't revert the cache. So now an attacker can still look at the cache and see what the secret value was. And the question that we want to solve is, how can we avoid such speculative leaks in software? And one solution to that is to just insert a fence here in line 3. And again, if you look at the execution, we still enter the then branch, execute this line. But then in the defense means we cannot go any further, and we have to wait until now the CPU. So the CPU cannot move on to line 4, which would then again encode the secret. So we have to go back to line 1, and we don't have encoded the secret into the cache. So now this is perfectly fine. We've solved the issue in a way. But the problem is that these fences impact performance even for non-speculative executions. So which means we want to insert only really necessary fences, or not fences in every branch. So I want to give you an overview of the tool CureSpec that we developed in order to do that. And the first step is we just make speculation visible. Then we mark possible fence positions. And these two steps are just there that we can now use an off-the-shelf model checker to check for vulnerabilities. Now, one possible outcome of this model check would be that we find actually a vulnerability, so we get unsafe. What we then do is we insert a fence which fixes this particular counterexample, and we then go on and check for another vulnerabilities. And this loop at some point will come to the conclusion that now the program is safe and we can return our safe program. So I want to now dive into the first step, which is speculation visible. I just depicted again the program. And what we do is we insert a special variable that now stands for whether we are speculating or not. And we initialize that to false. Then the branch actually becomes non-deterministic choice. And to account for now the when we are speculating and we are still in normal operation, we update this if the condition was wrong. And also for, in this case, line 3, where we for now assume that we know at this point there might be a leak, we also add an assertion that we don't want to speculate at that position. Now, when we have that, we go to the next step, which is marking possible fence position. And we just take for every position that we might want to add a fence, we insert a variable. Here we have 2 variables. And for that position where we want to or might add the fence, we add the assumption that the fence and speculation cannot happen at the same time. So now we have essentially done the whole build-up, and we can now check for vulnerabilities of that program. And we use SeaHorn for that, which internally uses set3. An important part here is that we are looking at infinite state system because this is software model checking. And I've depicted this infinite state space in this diagram on the right. Now, this assertion that we have here corresponds to a set of error states. And because this is infinite state model checking, we have an over-approximation of the program state, which is there to prove that the program is safe, but also a set of under-approximations that is there to show vulnerabilities. And in this case, we find a vulnerability, and this means that the under-approximation and the error states have an intersection. So what we now do is we insert a fence at the appropriate position, which means we set the fence variable to true, which means that at line 8 we would essentially stop speculation, and we cannot reach the assertion in line 9. Now what this changes the program now, right? So we get to a different program P prime, and one observation we have is that the over-approximation still is a valid over-approximation because we're only reducing the reachable states. So we can keep that. And this is important because this is the incremental part, so we don't have to restart from scratch every time. But of course, the under-approximation now is not valid anymore, and what we do is we just reset this to the set of initial states. So now we have done essentially one round of inserting a fence, and if these rounds is finalized, we get a final program. I want to again look at the evolution essentially from the initial program to how we model everything, and then to the final program. And the thing here is that we insert a fence at line 3, so fence 2, which means that we want to insert a fence before we access line 3 of the original program, which means we insert that fence exactly at that position. And another thing is that the model checker we use actually gives us inductive invariants that ensure that now our fixed program actually is free of speculative information leaks. So I want to recap shortly the whole method that we used. And I want to now come to the implementation of this thing, and want to talk about some optimization or choices you could make along the way. So first, there's the possibility to have different fence positions, which means, so one possibility is to just have a fence before every instruction. Another one is before memory instructions. And the third one is immediately after a branching instruction in both branches, essentially. This corresponds to just stopping speculation immediately after it started. On the other hand, we also have fence choices. So when we actually get a counterexample, which possible fence that is on this counter example path we might want to use. And a simple solution would just pick some, and then this counter example cannot happen anymore. But there's also a different one where you might want to just pick the last one before reaching the vulnerability. And, sorry. Also, for our implementation, we regard any memory operation as a potential leak. And now we can actually look into some innovation results. So we have here a set of benchmarks. The first four are AES encryptions from the OpenSSL library. And the first two are they just encrypt one block, and the others encrypt the whole array and chain each block with the CPC mode together. And the extension of CT means that this is the constant time version of that encryption algorithm. Then the middle part is also from the OpenSSL library, where this is like multiplication, squaring, and exponentiation of big numbers. And there's some minor problem there because we have to keep certain functions abstract, because otherwise the model would be so large that SeaHorn couldn't handle that. And the last benchmarks we used were from the Heckel star library, also just encryption and message authentication codes. Also, I've shown you a code example in this case, but in the actual implementation, we operate on the optimized LLVM IR level. So just use the code to simplify the presentation. Now, if you look at the baseline column, this was just picking some fence on the error path and also having possible, before every instruction, a fence. So it's like the most simple version you might want to look at. And in the hash-I column, I just record the number of instructions, which also corresponds to the possible number of fences. And the hash-F just depicts the actual number of fences that were inserted. Time is the run, or the average runtime of 3 runs in seconds, and RSS is the average maximum resident set size in gigabytes. And what we see here is that there are lots of fences inserted. It takes a lot of time. There are a lot of timeouts, which was 2 hours. And now we want to compare this to our more optimized versions of after branch and before memory. Also here, we note the number of branches and the number of memory operations, which also correspond to the maximum number of fences that you could insert. And the observation here is that there's a big reduction in the inserted fences and in the runtime. Yeah. We also did a second evaluation, which is the evaluation of how much fences actually incur an impact on the final program. And so what we did, we took 50 random seeds and then generated arrays from that. And this is depicted in the input size. So this is the size of that array that these functions operate on. And then we record the total time the non-fixed program took to execute that. And then also how the impact was for the both after branch and the before memory optimizations. And the thing here I want to say is that for some benchmarks there was actually only a small impact, but for others the impact is quite large, so that you cannot really tell beforehand what's a good way to go on. And the second thing is there's not a clear winner between after branch and before memory. So for some benchmarks the one is better, for some the other is better. So finally we can conclude we saw our method of CureSpec which is a combination of formal verification of speculative information leaks. This also is an automatic repair of Spectre leaks by inserting fences. And all in third, this gives formal guarantees with these inductive invariants. So with that, thank you for your attention, and I can answer your questions.
So we have some time for questions.
How do you handle loops?
We don't unroll loops because this is like SeaHorn by itself is essentially just software verification of loop programs.
No, you said how you handle loop, not how you unroll loops.
They're just, SeaHorn handles that by itself. So we don't do anything about loops.
The tool does. When you say we, you don't do anything special.
Yes, yes.
Possible to infer points where you need to infer fence as a result of some kind of analysis. So could you specify with some semantic property some way to set up this problem as an analysis problem in order to hopefully infer fewer fence points?
I'm not sure whether I got your question. You mean as a pre-processing step, or?
Well, if I understand well, right now you are using some strategy where you basically have a very basic syntactic criteria to decide, okay, we add a fence after a branch or before we read into the memory. And my question is, could you specify the property that you try to establish by adding fences in a way that lets you basically formulate as an analysis problem the question of inferring a bunch of fence points? So this way you would not have a syntactic criterion like this, but hopefully you would have a better performance overall. That's the question.
You mean also like inserting a bunch of fences at one point? Yeah. This would be totally different than this one, because this is built in the way that you insert one fence after the another. But yeah, sure, there might be a smart way to do that.
For your answer on loops, if you need a fence between the end of a loop and the next iteration, how are you going to handle that?
You mean, okay, maybe now I get your questions. The thing is, if SeaHorn finds a counterexample, then this is finite, which means essentially you have loop unrolling, and then you would see, okay, at one position I need to add a fence, and then you would insert that fence inside the loop, which then also removes like other.
It's a bit redundant, but you don't care.
It's not
You mean-
optimal.
Yeah,
You mean?
What if you only needed it in first iteration?
Yeah, okay. Yeah. Then, yeah, there might be a better way to. But then this is also, you could do just unroll the loop once as a kind of ad hoc optimization to see whether that helps. But yeah, I'm not sure. Because then it's also the question, what if it's second, third, or whatever constant number? Yeah. So we would insert the fence in the whole loop, and it would impact the performance for every iteration. Yeah.
I had maybe one more question about the experimental evaluation. I saw that you have out of sort of timeout number, but then your performance impact was 50%. So did you just set the time?
No,
the
the
baseline low, or did I misread it?
timeout was for the analysis of our tool,
I see.
and
Okay.
the runtime of the impact is
Okay.
on the actual code.
Clarifies. Thank you.
I think we can set up, and We can take the speaker again.